Hello, I'm Lou Bloomfield, and this is How Things Work. Today's topic, falling balls. You've seen your whole life that if you drop something, it plummets toward the earth. But what exactly is going on when that happens, and what does falling even mean? Is falling only when you drop something that was motionless initially, or does it also include objects that were already moving, maybe up or maybe at an angle? As we'll see, it turns out that all three of those cases, this one, and this one, are examples of falling. And they all fit into the same overarching concept. The idea that an object that's free of all outside forces, with the exception of the force due to gravity, accelerates toward the ground. Okay, to build that whole story, we have to start by looking at how gravity affects things. Up until now, which is to say, in the previous topic, skating, we had a situation where the skater spent most of the story with no force acting on him or her. A skater that's free of any forces, of any type and unnamed at this point, so the skater's free of any forces, moves at constant velocity. They're inertial. They coast. Those are actually all the different words for the same idea. So if you don't push on something, it coasts. If the skater is pushed on by something, the skater accelerates. The skater might speed up, slow down, or turn. Well, with the story of falling balls, we're looking at a force that we can name. The force due to gravity, and that has a specific name that we've heard forever, weight. Well, to give you an idea of what weight is, I want to start off by saying what it's not. It is not mass. So this ball has both a mass and a weight. To remind you, its mass is the measure of its inertia, how hard it is to make that ball accelerate. And so if I shake it back and forth, I am in effect measuring its mass, and not numerically, not quantitatively, but rather not very much mass. It's easy to make this thing accelerate. And mass has nothing to do with gravity. We could go anywhere in the universe, give this little baby a shake, and we would get the same mass. The mass doesn't depend on where the ball is. It's a feature of the mass, a feature of the ball. All right? What's gravity then? Gravity is really the source of the force. It's a phenomenon that we observe in our universe, that all objects pull on each other by way of this phenomenon we call gravity. And specifically, the Earth, which is the only thing big enough around us to exert noticeable gravitational forces on anything in our common experience, the Earth exerts a gravitational force on this ball. And the name for that force on the ball is the ball's weight. So if we can describe that we can name that force on the ball two ways. I can say the force that the Earth's gravity exerts on the ball, or the ball's weight. Obviously, the second one's the easier one, so I'll stick with that as often as I can. So the ball is experiencing a weight. Weight is a force. It is a downward force right toward the center of the Earth. And the amount of that force depends on the characteristics of the ball. And you've noticed in the past that a ball like this has a certain weight. And I guess I would judge that at a couple newtons. That's how hard it's being pulled down. And the way in which I'm making that measurement is not trivial. But I'm figuring it out, okay? On the other hand, if I take a ball like this, a little golf ball, less weight. So they're both experiencing their own weights. They both are being pulled downward by gravity, specifically the Earth's gravity. The baseball is experiencing a larger weight than the golf ball. So what determines how much weight each of these balls experience? Interestingly enough, and I'll come back to why it's interesting, the ball's weight depends on its mass. Remember, mass has nothing to do with gravity. Mass is just how hard it is to make something accelerate. And yet, this ball with more mass has more weight than this ball with less mass. More mass, you get more weight. And they go together and they go perfectly proportional to one another, which is a remarkable thing. There's no reason they had to go perfectly together. I mean, ultimately there is a reason. It's deeply rooted in the structure of the universe. But it could be different. It isn't. So, it turns out that everything here on the surface of the Earth experiences a weight, or develops a weight, or has a weight due to the Earth. And any object's weight, you included, is exactly proportional to the object's mass. Big, massive objects, ones that are very hard to accelerate, are also very heavy. That all may seem trivial. It's not trivial. It's a very sophisticated thing, or remarkable thing. And we'll see it has consequences for falling balls directly. Okay. So, it turns out that weight and mass are exactly proportional to one another. What's the constant of proportionality? That is, what do you multiply an object's mass by to get its weight? There should be a specific physical constant. And the physical constant, it's not truly constant. It depends a little bit on the strength of the Earth's gravity, which varies according to where you're located. Here, Charlottesville, on the ground, the strength of gravity is a certain amount. Gravity actually gets weaker, the Earth's gravity, as you get farther from the Earth. You got to go pretty far before it noticeably weakens. But even if you go up into the Shenandoah National Park and go a couple thousand feet up, the Earth's gravity is a little weaker there. So here it's a certain strength. And it turns out that the constant of proportionality is that every kilogram of mass, remember mass being the measure of inertia, every kilogram of mass develops or experiences about 9.8 newtons of gravitational force, of weight. So the constant of proportionality is 9.8 newtons per kilogram. Tell me the kilograms, I just multiply by that constant, and I'll give you the weight in newtons. So 9.8 newtons, it's not a fundamental constant that you would wax poetic about at some galactic conference. It's a feature of our Earth and the diameter and the mass and all that. And it varies. If you go to the moon, it's weaker. For example, the moon has gravity and objects develop weight, but because the moon's gravity is weaker than the Earth's gravity, for things having to do with the mass of the moon and its diameter, things on the moon develop only 1/6 as much weight despite having the same mass. So if I took this ball to the moon where the gravity is weaker, the constant of proportionality between the mass of the ball, which didn't change, and the weight of the ball, which depends on the moon's gravity, that constant proportionality would no longer be 9.8 newtons per kilogram. It would be about 1.6 newtons per kilogram. It's weaker. So if you want to lose weight, you can just go to the moon. You will genuinely lose weight by a factor of 6, which is it's a big win if you're trying to tick off some box, win a contest for losing the most weight. Obviously, it didn't have much real important effect. Okay, so I've observed that every object here at the surface of the Earth acquires a weight. What are the consequences of that weight? Well, if the ball in my hand is experiencing its weight, that is, it's being pulled down by a force, which we call its weight, but I'm pushing up on it. So I am spoiling the story by introducing another force that's somewhere down in our future, me pushing on the ball. But if I stop pushing on the ball and just let go, during that brief period, the ball experienced only one force, its weight. Nothing else. It was not inertial because an inertial object needs to experience 0 net force. This one was experiencing a non-zero net force, specifically its weight. Well, any object that is experiencing only its weight. Nothing else. That is to say, it's the net force on it is equal to its weight. If there's anything else involved, they all cancel. So eliminate everything else, just the weight. That is a falling object. And that's the most important definition of a falling object. A falling object is one that's experiencing only its weight. And when that happens, it accelerates. Because a force that's experiencing a net force, an object that's experiencing net force accelerates. Well, how much does it accelerate? The acceleration of the ball when you let go and drop it. First of all, I should point out that it really is accelerating. It's accelerating downward. It's going faster and faster in the downward direction, which means that its velocity is going from, if I drop it from rest, its velocity goes from 0 to a little bit downward, a little more downward, still more downward, and so on until I run out of room. So it's clearly developing a downward velocity by way of a downward acceleration that's allowed to proceed for some amount of time. So how much is it accelerating? Well, that depends on two things. It depends on how hard the force acting on it pushes. In this case, the weight. Well, how big is the weight? That matters. The bigger the weight, the more the acceleration. But there's another feature, another physical quantity that enters into that acceleration idea. That the ball, when you let go of it, yeah, it's pulled downward, but that doesn't mean that it instantly goes to infinite downward speed. Poof, gone. No, it's got a mass, and mass resists acceleration. So its acceleration is the downward force on it, namely its weight, divided by its mass. Force over mass. In this case, it's weight over mass, but weight is, weight, spelled with an E-I-G-H-T, weight is proportional to mass. So that means that this ball, which has, of course, a certain mass, develops a weight that's proportional to that mass. If you take the weight and divide it by the mass, there's a mass associated with it developing weight, and there's a mass that you're dividing by. The masses cancel. And what you end up with, the downward acceleration of this ball, the force on it over its mass, is just that constant of proportionality that we encountered previously that relates the ball's weight to its mass. Remember, every kilogram here on Earth develops 9.8 newtons of downward weight. So when I let go of this ball, it accelerates downward, and the acceleration downward is the ball's weight divided by the ball's mass. The ball's weight is 9.8 newtons per meter times its mass. So if I take the weight and divide it by the mass that I just introduced, I'm doing verbal algebra, which is a nightmare. I realize you'll go like, what is he talking about? But I'll do my best, and you can look in the book or on the slides for this little calculation. But to reiterate, we're going to divide the ball's weight, which we can write as 9.8 newtons per kilogram times the ball's mass. We're going to take that weight, and we're going to divide it by the ball's mass. In that case, I've got mass divided by mass. They cancel. The ball's mass divided by the ball's mass, that's 1. So the ball's downward acceleration, its weight over its mass, is 9.8 newtons per kilogram. 9.8 newtons per kilogram, that's a strange thing. That's a strange quantity. It doesn't sound like an acceleration, which is what it's supposed to be. It turns out that newtons per kilogram that's an assembly of composite units. The newton is not a fundamental unit in nature. It's not like the second. The newton is a constructed quantity that is equivalent to a kilogram meter per second squared. Is that true? Boy, plan ahead here. Kilogram meter per second squared. That is indeed correct. And if you divide that by a kilogram, you end up with a meter per second squared, which is the standard SI unit of acceleration. So if I have completely dusted you at this point, the observation is this, that when I take a ball like this and I drop it, it accelerates downward in proportion to its weight over its mass. And if I compare that to the effect on a littler ball, which has less weight and less mass, that ratio is the same. So the big ball, like this one, the baseball, yes, it has more weight, and that by itself would make it accelerate downward faster. But it also has more mass, and that by itself would make it accelerate downward slower. So in going from a little ball like the golf ball to the big ball, I have cranked up the weight and I have cranked up the mass, and those increases cancel one another. The two balls accelerate downward at the same rate. They acquire downward velocity at the same rate. So I can show you that here. Ta-da, it's video. Ready? Boom! They hit together. They both, in slow motion, human animation here. I could do it real, yeah, but then I'd be into like big time production. They go faster and faster and faster and faster, and they smack together. And that is a very general observation, that in the absence of nuisance effects, the most important one of which being air resistance, when you drop stuff here on the surface of the earth, it all falls together. The big things with lots of mass also have lots of weight. And so they're pulled down harder, but they resist acceleration harder, and it all cancels out. So you can throw everything in your pocketbook out, off the cliff at the same time, whoo, down it goes. To the extent that it doesn't encounter air resistance problems, it will all plummet together and hit together. So that means for all the balls that you encounter, with the exception of things like a beach ball, which has a lot of air resistance problems, or a Nerf ball, they all just go together. Throw them all out. And you get very used to, from experience, catching things coming at you. You know how they fall, because they all fall the way you've seen everything else fall in life. This behavior, where if I drop a sheet of paper and a ball, and they don't fall together, yeah, that's an air resistance problem. So neglecting that, life is pretty simple here. So that's falling, and particularly falling from rest. You sort of can watch the ball start with no downward velocity at all and get more and more and more and more downward velocity. And to say a few cents about where the ball is, well, first off, how the acceleration behaves with time, how the velocity behaves with time, and how the position of the ball behaves with time. It's pretty straightforward. You can get lost in the mathematics of this. It's the kind of thing that a conventional physics course might well dwell on for days. So I want to do it very quickly. When you let go of the ball and it begins to fall, the only force acting on it is its weight. And that never changes during its descent. So the ball's mass stays the same, the ball's weight stays the same. The ratio of those two, weight over mass, never changes, and therefore neither does its acceleration. So the ball's acceleration, from the moment you release it and the moment it becomes a falling object, only force on it being its weight, from that moment until it hits the ground or whatever, it is accelerating straight down toward the center of the earth at 9.8 meters per second squared. Steady, constant acceleration, nothing changed about it. So far, that's acceleration. Now how about velocity? Well, velocity is not constant. Why not? Because the acceleration would have to be zero for the velocity to stay constant. And the acceleration is not zero. It's this downward acceleration, what's called the acceleration due to gravity. That's the fancy name for this 9.8 meters per second squared that we have just observed. So the ball is accelerating downward at the acceleration due to gravity. And as a consequence, its velocity is increasing in the downward direction. With every passing second, the ball develops an additional 9.8 meters per second of downward velocity. It started at zero velocity. Then if that's the case, and at the moment that's what I'm saying, then after 1 second, the ball will be heading straight down at 9.8 meters per second. After 2 seconds, it'll have doubled that. It will be at 19.6. Now you test my mental math. 19.6 meters per second. And after 3 seconds, the ball's velocity will be 29.4 meters per second downward. So far, so good. That's for velocity. How about position? Ooh, position's complicated because the ball is covering more and more distance with every passing second. So in the first second, it doesn't go very far. It wasn't traveling very fast on average. How fast on average? Well, actually, it started the second motionless, which is a total loss, and it ended the second traveling downward at 9.8 meters per second. So its average speed over that first second was halfway between those two values, or about 4.9 meters per second. That's the average speed of the ball during that early times, the first second. And it only covers, in that first second, 4.9 meters. So the ball travels a little distance. It's not little, but it's, on the grand scheme of things that you'll see it's little. The second, the ball travels a lot farther. Why? Because it started that second already moving downward. And it finishes that second traveling not quite fast downward. And it turns out that in the second, the ball travels 3 times as far as it did in the first second. How about the third second? This time it travels 5 times as far as it did in that first second, and so on. So with each passing second, the ball travels farther and farther. And this, for example, this surging increase in how far down it goes. This is why you don't drop things for very long amounts of time. They cover too much distance. So a bungee jump, for example, it's easy to make a bungee jump event where you fall for 2 seconds. But to make a bungee jump event where you fall for 10 seconds, oh, that's tough, because you're going to travel a long way in that 10 seconds, and you had better have started pretty high. Okay, so that's the story of falling from rest. How about other possibilities? Remember, the concept of falling, a falling ball is anyone that's experiencing only its weight. And that doesn't require it to be starting from rest and heading straight down. It could be heading up. So when that happens, this is a falling ball, not yet, now. So on the way up, it's still a falling ball. It was accelerating downward toward the center of the Earth at 9.8 meters per second squared, the famous acceleration due to gravity. But the weird thing was, it had an upward initial velocity. It was heading up. Somebody threw it, me. And so it started the story with an upward velocity, but as it accelerated downward, it lost that upward velocity. A downward acceleration, when you're moving upward, sucks the upward motion out of you. And that's, I'm using that cavalierly. We'll eventually get a name for the sort of the quantity of motion that you're carrying with you that's being sucked out. And the name for that, secretly, don't tell anyone yet, it's called momentum. Okay? So you start with this upward momentum, and it gets sucked out of you. So, okay, up goes the ball. That, of course, assumed you are the ball, or having a ball, or I'll stop. Okay, so the ball starts the story now heading upward. And as it does, as it rises, it is indeed accelerating downward. And that means that it's losing its upward velocity. It's going more and more slowly. There will be a moment where it comes to an absolutely zero velocity. There's an instant in time in which it is not moving up or down, after which it begins to descend. So at that peak, it is momentarily motionless. It is still accelerating, even at that special magic peak moment. So it is not a constant velocity up there, not a constant velocity of zero. It's an instant of being at zero on its way from heading up to heading down. Just as if I move to the right while accelerating to the left, there is a moment when I'm motionless and then I go back the other way. And right at that moment, for just that instant, I run out of rightward or leftward velocity. I'm just down to dead zero. But that doesn't mean that I'm not accelerating, that my velocity isn't changing. It's going from heading to the right to heading to the left, and that's just the instant where it's sort of passing through zero. Okay, so a ball that is tossed straight up rises more and more slowly with the passing time, comes momentarily to a stop, and then begins to descend. And once it begins to descend, the story is exactly the same as the one I already told you about. It descends as if you were up there releasing it from rest. So it goes through a rising motion and then a falling motion. And they're remarkably symmetric. Throughout the process of rising and falling, the acceleration is always straight down at the acceleration of gravity, and the ball goes slower and slower and slower, faster and faster and faster. It's just, it maps up and then it maps down. And if you watch that video in reverse, and I've done this before, you can't tell forward from backward. It's a symmetric motion, symmetric in time. So that's a ball falling from heading straight up. How about if the ball fell from heading at an angle, like this? The physicists like to call that projectile motion. For most people who like to play sports, it's called throwing the ball, okay? Most people, yeah, I mean, unless you're bored and by yourself, throwing the ball straight up and down all day is kind of dull, okay? If you're playing with other people and you're not completely, self-indulgent, whatever, nincompoop, you throw it to them or they throw it to you. And when you do this, the ball travels in this lovely arc. What describes that arc? What's going on here? It turns out that the story is surprisingly simple. Gravity acts strictly downward. And so it affects the vertical motion of the ball, how it rises and falls. But gravity, because it acts straight up, doesn't give a hoot about the ball's horizontal motion. There's no push on the ball left, right, toward you, away from you. So the ball's motion, when I throw it at an angle, divides beautifully into two simultaneous things. In the vertical direction, so if you just completely ignore where the ball is, left, right, toward you, away from you, if you just watch the vertical motion of the ball, it does the usual rising to a peak and then coming back down. It's accelerating downward and it's doing the usual business of losing upward velocity, coming momentarily to zero upward velocity, and then it descends faster and faster, more and more downward velocity. That's the vertical motion of a falling object. The horizontal motion is that of an inertial object, a coasting object. Horizontally, there's nothing slowing or speeding up the ball, so it just does what it was doing. And it covers equal downfield distances in the direction of its travel in equal times, coasting steadily along. And if you combine those two ideas, vertical rising and falling, that of a falling object, with horizontal coasting, this is why I had two balls. Got a whole box full over there. If you combine those two, the coasting horizontally with the rising and falling vertically, you get these arcs. And those arcs, for anybody who's played sports, you know and love these arcs. This is the shooting the basket. You're exploiting that arc. Throwing the field goal. Yeah, I'm a good sports guy. Throwing the touchdown pass. That arc, you know this thing. It comes naturally. You're used to knowing how it propagates and where to go to catch the ball. So that is the story of falling balls, and it applies not this idea of falling applies not just to balls, of course. It's to anything that falls in the absence of air resistance problems and such that sort of add complexity to the story. And so hopefully that pretty well explains the story.